Hello, I'm Shadow of Shadow Gaming, bringing you episode 16? Yeah, episode 16 of Programming with Shadow. In today's video, we're going to look at a concept called polymorphism, particular parametric polymorphism. In C Sharp, this is called generics. And last time we created what I was calling a dynamic array. For this dynamic array, we data type, you give it everything's integers, so values are integers we give to the add to it and the array and that. We could do that. That works. We wanted a different type, like say we want to add strings to the list, we'd have to create an array of. We have to redo this with strings. But we're going to look at today is another way to do that. And as I said, that's called parametric polymorphism. So the idea is that the parameters are changing. We mentioned in the object-oriented programming, polymorphism is the idea that something can be something else. So you can do something one way and then with a different context that you can do it another way. That's exactly what we're going to look at today. Let's do this. Do export. I think it's start. You just do this. Let's not. I was going to just make a copy of this. Well, let's not. Let's do this. Let's do cd dot dot. Make directory generic array cd generic. Now let's do .NET new console. ls. Now let's just do code dot here. I'll just copy over the code. Do this, Control A, Control C. It's hiding behind my microphone. 4. Dynamic array, let's add a file. Array.cs. Go. Program here, let's copy it. Control A, Control C. Remove this. All right, there we go. Now I can at least see VS Code is not hiding behind microphone now. Close that. Big. Let's go ahead and run this because it takes so long on the first run. So there, we've copied over what we had before. So we have an array of integers. They're a dynamic array of integers. Let's runs. So let's make an adjustment. So generic are a way to just say, okay, this is generic to whatever type we say it is. So what we can do is it'll overrun. Just pausing, just calling now for it to run. Maybe. You know. Well, we're going to go ahead and edit this while we're here. There we go. Finally. So there. Now we've ran it. Okay. So to make something generic, it's actually really easy in C Sharp. So you might hear this as templates in other languages, generics in some languages. All we're going to do is we're going to add angle brackets and a T here. And this T doesn't have to be a T. You could use another letter there if you wanted to. T is just sort of the standard. If you look at the docu, that's what it's going to say. And I would say that's what people's going to expect. So there, we made it a dynamic array of T. Now if we go over here and look, it's they're using the generic type dynamic. T requires one type argument. What we can do there is do a T there, but T doesn't work in this situation because you have to specify the type. But now we would say int. There we go. So now we've recreated what we had before. sort of. One issue here. We're going to get the same output, so I don't know why it's taking so long, but we're not actually using the T anywhere. So right now it's still, it is generic, but we're not actually using generic. So what you would do there is you go in here and say this. There we go. So now it's not actually generic. And you see here there's some. Now, so right now we've got a generic array here. So XT, so a generic array of data. And what this is, we're trying to return an integer. We don't have any guarantee it's an integer. Fix that by saying T there. We're going to have to do that in a couple spots. Down here, again, we're putting in data, which is an int. Not an int, it else. Here we're doing it. Go. Here's another. And by the way, I'm finding these easily. Oh, if you look over here on the side, highlighted here too, but there's red highlights here. Those indicate an error. The orange here indicates a warning, telling me that this could be null. So the null, which it can be. If you notice, that probably wasn't there before we put data. Now that data can be a T, it can be null. Let's see, same thing here. New array. There we go. That's the last error. So we'll come back to fixing this one. So let's see what happens now. Now it's really using the integer we say here. So we're saying, okay, give me a dynamic array and the type's integer. And that's not interesting, but we have the same array. Same out. Let's see. So that was really easy to convert. So all we had to do is change places where there was an int to a T. And this, notice I didn't change all the ints. That's because these are different things. These are data and they're coming back as integers, so the capacity is still an int, the count's still an int. Type of the data is no longer an int. And to show that more fully, let's do this. There we have an integer array. Let's make it something else. Let's do a string. I do string because it's a lot different than an integer, but there we go. And that's all we needed to change. Now we have a dynamic array of 3 strings. Let's just copy this. Let's do this. There we go. And now if we do a dynamic array dot print, we converted it to an int, from an int to a string that easily. You can see some resizing here. There we go. Very nice, very quick. So that could be used for other types here. In fact, anything we want to put in here, we can technically, we say So there, anything that's an object can go, and of course string's an object, so object works. There we go. Let's go back to string. Try something else. So you've seen that null warning. Let's see what happens if we give it a null. So this exclamation point set tells the compiler, okay, I know what I'm doing. In this case, what we're doing is going to be wrong, and I want to see we're going to get an error, I believe. So that tells the compiler, okay, I know what I'm doing. Don't tell me what to do. Look, it worked. So what happened there, that this warning is an actual warning. So since it's null, or anything actually get appended? Yeah. There's something here, but it's a null, so null's nothing. You can tell that by there being a comma and space here at the end. Yeah, so that actually works. So if the first bit of data was null, I think it would do this. Now, let's see what happens. And there we go. No referencing. So that's just saying that we didn't expect the first one to be null, and it shouldn't have been. So what we can do here instead is if it's null, that. Now, let's it. This says if it's null, don't do this. This says if it's null, just equals. Do I even need that? Wait a minute. Let me just do it. Nah, better not. There. So that'll work now. Maybe that's what we want to do. Maybe it's not. There you can see it's in here, but it still works. So this supports other types too. Like if there's something else we want to do, we want you. Say we want the U long. Let's say we want. I'm just spamming keys and no reasoning for this. Just add some numbers. There we converted it to a U long array, and it was that easy. That can be really powerful. There's some big numbers. That can be really powerful because, as you've seen, there was very few changes we actually had to do over here in the dynamic array. Let's see. So, just to recap, this angle brackets and then some later. Like I said, T is common, but you can do other things as well. That's all it takes to do generics in C#. Really easy. This is showing all this. This is showing this with our dynamic array we created ourselves. This is actually built into C#. So what we could do, in addition to this, is we could do the list of U long. We'll call it dynamic array just for the sake of it. Now let's come here and control C, copy, control K, C, control V. There's no print, so we'll have to do our own print. Let's just do it. Let's do a local function. Do void print. We're not going to do static this time. let's just say let's just copy the. I was gonna do my own, but I was like, I want the same. Do dynamic array.count. Copy. There we go. There we have a print. Let's do print. There we go. I think we should see a very similar to run the last one. There we go. You don't see all the additions, but that's happening in the background as well. That's using a built-in type of list. So if this doesn't work, you might have to have some using. So errors are being hidden. Implicit using, let's disable this just a sec. So that says implicit using means there's some specific ones it already knows about, and it's handling them in the background for you. If you turn that off, however, it won't handle that. Now we need to come in here and do we're doing a control dot, do using system. We go over here. We're going to use systems collection dot generic. That should be at the top of the file, but because I have comments, it doesn't know how to handle a comment. So this is we've been doing it implicitly before, but here we're using the system.collections.generic library. That's where we get list of T. If you look here at the docu, I think it'll even say it tells me what type it is. If you go look on online though, list of T is what you're they're using its collection to do the exact same thing here we're doing in dynamic array. The dynamic array we also had to add a using here. That's just to handle coming out just that's a handle index out of range. It's from the system. Console write lines, they're all from system. And that's all. They're from the using system library. And that does a lot of things provided to you by the .NET SDK. Here's something that we don't see with ours, but we do see with this. This is offering us that we could collection initialization can be simplified. We've already seen this before, but let's do that again. There we go. What we can do better, we can even do this. Am I wrong? Might be wrong on this one actually. Oh, I guess I can't where I have to tell it the size. If we do the size, then can we? Yeah. There we go. There, we're declaring this the exact same thing here as we did with all these ads, but we're doing it instant. And there's cases for both of that. Because now if we were going on down here and running the program, we could do something like we could get a number from somewhere else and we could do add. Like maybe we have some default values and we need to add 42. String, not a string. There, we could add 42, and now if we print it again, you'll see 42 in the. It's the second time. Field code was my error. I need system here as well. There we go. Now, if we look here at the end, again, I can get behind my microphone, but there's a 42 back there, right over here. So yeah, so played around with a dynamic array, but C#'s already got that built in. Someone else needed it before as well. In some other languages, this might be called something else. For example, in Java, it's a array list. In Python, it might be a list. In C++, it might be a vector. But all these are just sort of the same idea, a dynamic array, and most of them are the same generic dynamic array. One thing I'll mention here is that C# actually has an array list as well, and you might occasionally run into it as well. Array list is not as nice. So it seems like it's very similar to the same thing. If we look at the add here, though, adding an object. And you can do some things with this, and you'll occasionally run into it. But you're just setting yourself up for trouble most of the time. You usually want to have a good reason to use it. So list is what you're actually looking at, not array. Oh, my great timing. And I feel like I haven't covered anything with this. So we have a list here, and it's possible, but we're going to go back to using the other array, however. Just comment this out. Show this one again. We're going to use errors, and we're going to do a little more with. We're going to do a little more here. All right, so let's see what else we can do with a generic. So background. Nothing I want. So let's say whatever type we're doing, say we intend for it to be maybe just be numbers, or I believe we can set that. I'm trying to find the syntax for it on docu, but I'm not actually seeing it. I'm completely failing on finding the docu right at the moment. Okay, the page called Constraints on Type Parameters for Programming Guide. So what we can do is we can constrain our dynamic array here. So what we would do is, let's say we only want it to be, right now we can put, as we said, we can put objects in. Let's say where t struct. What this set indicates is where t is a struct. We haven't talked about structs yet. Structs are a special type. If you look here, int is a struct. Mary Ulongs are a struct. String. Yeah, string is not. String is object. You can see by class. So class and struct. That restricts it though, but so that we can only put structured values. So let's say we do byte. That'll work. The other types will too. Or way too big. There we go. So that's something you can do too. And there's a whole bunch of different things you can do here. We can say where it's a struct, where it's a class, nullable class. Can we go nullable struct? That's not available. So nullable class though, we can say not null. Can't spell. So that'll get rid of the null case we had before. Let's say null here. Now it's an error. And if we say do it anyway, the compiler's not going to let us get by with it now because we said not null. Oh, there it is there. Yeah, so without that, you can see it doesn't like that. Oh, okay, no, it doesn't. It's just a string. I guess byte doesn't work because it's a because it is a struct. So let's do string. Here, I'm just going to delete these, but just because there's so many that changing. So there we go. So now we're going to get the error again. Not. Oh, we handled it. We said that if it gives us an error to give you a 0. Let's do where t not null. I read that where t is not null, but that's not technically an is. There's actually an is keyword. It's actually going to let us since we do. That lets us. There we go. Now it gives us a warning. So interesting. I thought that might actually stop it, but I guess it doesn't. Some other ones. Let's see. There's also unmanaged. I'm not going to go into that one. Where new. That one's interesting. That just says it has to be a t where there's a top, where the top has some kind of has an empty constructor, a parameterless constructor, new whatever top. There's actually a whole bunch of these. Let's see. There's a where you can do from a base class, where you can do from an interface. Where you can do t of u. Guess you have to pass in new here. So this says where t up here is of whatever type this is. Again, that's just this could be anything you want here. You just have to remember that anywhere you would use it, you would do goes up like that after that. But you can, or like I said, the common things U and T. You just go from there. Like B would be the next one. You can be more descriptive with it, and that would be a good thing most of the time. A lot of times, though, most of the time I've actually seen something generic. It's just been T, and that's good enough. Let's see. Anything else? Default. Default. T default and like this. Valid on override and explicit interface method. I might have to go figure that one out myself. I actually don't know if I know what that does actually. Thought it was going to say where there's a default value, but maybe not. Some places what you can't do. Let's do multiple. Try that. Let's see. Struct class. Not like that. Yeah, matnop can do multiple. I don't see anything else here that's pressing for us to cover. Just a good thing to know is that you can do something like so, and you can control, or you can use it to control from dynamic type or your generic type more easily. Um, if we have two types here, like if we have a U here, do this. They don't have to match. You could constrain multiple types. And I actually haven't actually seen multiple generics like this by default. Yes, I've used them, but I've never actually seen them actually created in non like in the system generic library or somewhere. But you could do this and you can have multiple. I'd say there's a limit eventually, but I actually don't know what it is. It's apparently a big limit, whatever it might be. Rid of all except that. Anything else? Yeah, that looks like about all the generic. So you can use that. So what this is it's saying it's a dynamic array of whatever type we have, where type is a struct. So that's pretty much what I wanted to cover in this. It may actually be done. Switches to class, then okay. That leaves me with one question. What happens if we do this? Let's say this is a uint. Yeah, uint, since it's struct, isn't a valid type. It must be a reference type in order to act as T in this. Interesting. Okay. Let's do that. Turn these back to strings. So yeah, I think that's actually going to do it for this lesson. Very short, relatively, but it gives us a good starting place and for generic types, and I'll see them in an upcoming project. So yeah, let's recap. So in today's lesson, we've taken our previous dynamic array, we've made it generic. And generic in C# is pretty simple. You just add this, and then anywhere you're going to use whatever type you're going to put in there, that type. So this used to be an integer array. We made it a type. And we did it here, here, did it here for data we're adding, here for data we're adding, and here. But all in all, not all that many changes to make this a lot more powerful. So now we were able to add more things here, and whatever we added is what it became, and we didn't have to go through and change the dynamic array anymore. And we also looked at constraints very briefly. I will say I have only used constraints a time or two, so I won't say they're that common. That being said, I haven't used generics all that commonly either. I used them a little bit, but not a ton. But they do come up occasionally, and they're good to know. They can be really useful for what they are, because say you need to do a dynamic array, so something of multiple types. Well, here instead of having to recreate it for each type, we were able to recreate it once, just reuse the type. The constraints, the where type is a class or construct or whatever is just a way to constrain what you can put into it. That can be useful as well. Like if you have special handling, like maybe you're doing some math, you should be able to do there. Like maybe you have a base type of math and everything inherits from it, so it has the same operations, something like that, and that would work. We also looked at using statements. So this is just a C# way of saying, okay, I'm using system, using we're using the console class here. Using system.console down here to write on. This is just importing it. We're importing this here for list of t. We also looked at that. That's a built-in type that's basically a dynamic array. Basically, this dynamic array we created is simply just a list of t here. And it's best to just use the built-in one because then everything works. And if you find cases that it doesn't work, that's when you would look into building your own. But for the most part, list of t is what you want for most. So yeah, so that's going to be the main portion of the lesson. So I'm going to do the regular ending part here. So the next lesson we're going to keep looking a little more, and we're going to look at another concept called enumerables. They can get really deep, but we're going to just hit the highlights like we've done here. But that's going to be the next lesson, I think, unless we do maybe I have an inspiration and we'll do a project. That's the intention. So I'm going to call that the end of the lesson here, but I am going to move into one more thing. This is I say more mathy side of things, but it's not really math. It's just interesting to me. So what we're going to do is we're going to do some complexity analysis. The idea here is as we add more and more of things to the array, what happens to it? Does it get slower? Does it happen, and how does it do it? The idea there is something called complexity analysis. In programming, you use you use functions of growth. So, not remember from an algebra class or something. Basically, some functions grow faster than others, and in programming, you can use that to describe your algorithm. So, array is really easy, but we're going to treat this as an array, but it's similar concept. So, capacity, we store this off. It's really easy. So we would say this is read big O of 1. That stands for big O of a constant. So it's always constant. So no matter how big the array is, the capacity should be the same here. And the count's the same. No matter what we do, it should take the same amount of time, no matter how many values there are. And the creation here, same thing roughly. Actually don't know how arrays initialized. My suspicion is that it clears everything, so it has to create the array and then clear all the space. So I would estimate that this is big O of n. That stands for linear. So saying it's growing at linear time. So you could read that as if there's a 1, exponent 1, but do that. But that's how I think it would do. Index here is a little more interesting. Let's do it. So index, so to find something in an array, you have to search through everything unless you do something fancy like a binary search, right? But not with an index. So index, you just say, okay, give me this position. If the position doesn't exist, then we throw an exception. Otherwise, just do the position. This is big O of 1 and it's constant. So now we could do a little more thought though. And there's a lot more thought that goes into this. C# is a high level language, so a lot of things can go on behind the scenes, but for our purposes, we could say, okay, so here we do one operation here, so we check the count, check if the index is greater than count, then we go on, we return data. So two operations. So one, so that's the second operation. In reality, that still, no matter how many times we do this, it should still be the same thing. In fact, even if we hit the throw exception, it's still just 2 steps. So it's still a constant time, constantly taking 2 steps. So when you do the algorithm analysis, you don't necessarily care exactly how many steps it takes. Maybe you do if it's a really large number, but for the most part, you care about what takes the longest. Do that here in just a second. Add, yeah, next. So add. Well, here we do one, write something to the console. Here we do a check. Let's say that's less than, so here 3, 4. There we go. So, and that would always be the case. So 5. So that looks constant. Let's do that. So without resize, it's constant. With resize, however, some things change. So for that, so let's do resize. So second one's resize. 2. Now we're in here though. 3. I want to say this is a fourth one here that we're going to have to step in. How much? So the question is, how much does resize take? Step in the resize. What I did there, clicked on this and I pressed F12. You can also control click. That takes you to wherever you're going. There's a lot of things happening. I should have broken this. But here, so we're inside here. So this is a 1. This is a 2. This is a 3. And notice each one, I'm counting each one of them separately because they really need to be. It does this one first, and then it checks, does some short circuiting here, like this one's false. It knows it's done and doesn't have to worry about doing this. Not, it does this and then checks. So 1, 2, 3, 4 or 5 depending on 2. So this might be a 5 or 6 by itself. Create a new one. We already said that I'm not 100% sure on what this is, but I think it's going to be big O of n, so linear. Here's the interesting bit though. This one's just a 1, so we'll just say +1. Here though, we have to look through the entire array. So it's just moving all the array in each time. So here we're linearly going through the array. So this one's definitely big O of n. Even if this one isn't, but I think this one is. Even if this one isn't big O of n, though, this one. Here's a 1. +1. Let's do. I'm just going to say this is 6 for the sake of example. So this does +1, but it does it +1 each time. So +1 up to n. So once again, this is done big O of n. So let's get even more technical. So this happens once. These two happen for each loop. So it would be what? 1, 2 big O of n. So you see suddenly their count's getting pretty big. 1 +1. Suddenly let's add these up. So 2, 3, 4, 4n plus 6 7 8 9. So this one's a 10. We'll say 10. So there we go. So we can say that this is big O of 4n plus 10. However, that isn't really what you would do. So you're only really concerned with the largest term. Like I said, you might be more concerned, like, say if this was a 10 billion, then yeah, maybe you suddenly care about that. But for the most part, you're concerned with the largest term, so then you would do. However, this still isn't final form because is there any major difference? Let's say n's 1,000. Is there any major difference between 1,000 and 4,000? And the answer in this case is probably not. On the order of operation side of things, the computer's going to go through them at similar speeds. Or 4,000 is going to be smaller, but again, as long as this coefficient here isn't too large, it's not going to matter all that much. So the final form here is this is big O of n. There, go back to add wherever add is. Now no, the resize is notice I've completely done this a different way, but now we would do let's just add these up. Say 1, 2, 3, 4, and the fourth one here is just for the function call. 4, 5, 6, 7. So we would say n plus 7. We happen to know this was a 4 and this was a 10. This is all coming from the inside, but that again implies that this becomes 4n plus 17. 17 is irrelevant. 4 is irrelevant. Therefore, yeah, big O of n. One thing there, so even if my count's right, which it is not, like I said, these break into a lot more smaller pieces when you actually go down the list, but you can use it as a good feel for how long it's going to take. So even if we do these 17 steps, so what's the breakpoint? So if we do 4 here, 10 plus 4, so if we have 4 elements, it takes more to do the other steps. If we have 5 here, then it's 20 versus 17, so suddenly, you see, just by having 5 elements, we're already doing more work. Let's say n's a really big number. Let's say it's 4 billion. Let's say it's a billion again. Then you got 4 billion versus 17. Suddenly, yeah, the n suddenly matters a lot more. And that's the idea with between big O analysis or complexity analysis. No add item here is n for each item in data, so we know this is an n. That's interesting though. That definitely means we should clean this up and not do it this way, because this says we have to loop through each of these. That's not how we want to do it. So this becomes n squared. That's not what we want to do here. Here's our own resize. See, we already know we've resized it properly. We did the resize once, so add's just going to be, yeah, so add's going to be constant time because we did the resize, so it isn't hardly as bad. So it's still going to be big O of n, but if I hadn't done this, it would have sucked a little more. Yeah, I still don't think this is good. This is a good way to do this. I should have thought a little more and just did it. Just chose to do it on the fly last time. And remove that. So remove that. Again, we can look at this and say this is a 1. This is 3, but 1, 2, n. N minus 1, but the minus, again, the minus 1 tails off for the n. There's 1. So this one is big O of n. And print 1, 1, 1, 2, n. Big O of n. Noticing a trend here. A lot of array operations are either constant time or big O of n. Let's look forward one thing. I don't suppose. I might post a link in the video description if I find what I'm looking for, but a quick Google search did not reveal to me what I'm looking for. Yeah, so that's in a way to say how fast things grow. I really like to find this. Yeah, I'll have to search it. My searches are not doing wonderful for finding what page I'm looking for. But it's just a way to describe how big an algorithm, how fast an algorithm grows, and that is you can you can use it to know page, and that is you can use it to know how slow something could be. Like if you have a ton of values. And we'll do a lot more of this as we start getting in the other function or other types. But we can see somehow page here. Here's how they grow, and you can see here's good, and as stuff gets bigger. Linear's here, logarithmics here. This is like the binary search we did. It's logarithmics, pretty good. You notice things get out of hand very quickly. Those you get higher up here. Here's n squared. N cubed would be like in between here and all the other n's you could have possibly here. Well, these are huge. These are exponential factorial. Here's what I was looking for. So I'm not doing a binary search for binary searching, but array access we said is constant. I believe that's what we found. See? Yeah, constant. Search big O of n. You have to linear search, or you can do logarithmic if it's sorted. That's an important distinction. Insertion big O of n. Insertion was O of n. And these are worst case. So in worst case, you'd have to resize. So big O stands for worst case. There's other designations you can have. You can have best case, worst case, average case, but worst case is usually what you want to do because if it's all right in worst case, you don't usually care about what it is in the best case. And deletions big O of n, as we've seen. So average and worst are the same is for all of these. Space complexity. I haven't mentioned this. What we're looking at is time complexity, how much it takes to compute. Space complexity is just how much memory it takes. So it's linear. You have to have space for every element of the array. It's actually a little more than that because you also have to have the space for the capacity and count, but effectively it's how much every element is. So yeah, good page to remember. If you like this kind of thing, you can look through it and learn a little more, and you'll see over time we're going to look into a lot of these different topics. as we move more into algorithms and data structure side of things, these are data structures, we'll start seeing a lot more of these and see if we get the same numbers here. If we don't, our implementation's wrong. But I'll leave that. Like I said, I'll try to remember to put that in the description. But that, I'm going to leave it there. So this was a good aside. Like I said, we'll look into this more in the future, but I just wanted to do that since we had time, and this felt like a good spot to at least go over it once, and we'll go over it more in depth in later lessons. So, thanks for watching. Have a wonderful day.